All right, so now that we have taken a look at our basic trig ratios and we started to look at our unit circle, now we are going to get into the graphs of sine and cosine. And then we'll get into tangent as well as the reciprocal functions as well. One little note as we move on here, this is meant to kind of be over 2 days that we're going to be doing this. I'll kind of give you a heads up that this is going to be a little bit of a longer video, so you may do part of it one day and part of it another day. Maybe you do the video all one day and then you work on the assignment the next day, but know that section 5-7 is meant to take probably about 2 days at home. So just kind of keep that in mind. There is also a piece of paper that you should have with your materials that's working with the Ferris wheel problem that you're going to need to have. So with that being said, we're going to go ahead and move on here and take a look at the graphs of sine and cosine, and then take a look at how can we use transformations to graph these out as well. So there is a Ferris wheel problem that you should have with all your materials. And a little bit of information here. This is working with the London Eye. It's the world's largest Ferris wheel. It's located in London. It's 450 feet in diameter, carries up to 800 passengers at once in these little capsules that you see right here. And they kind of, if you notice, they've got little tracks right here that kind of go around the Ferris wheel, so you're always level to the ground. You're never upside down or anything like that. And turns continuously. It completes a single rotation once every 30 minutes. And it's slow enough for people to hop on and off while it turns down at the base of the Ferris wheel. And for our purposes here, we are going to be treating it like we're getting on, obviously, at the base here. And we're going to be going counterclockwise as we think about this for our purposes here. And then later on, we'll talk about going, clockwise too. But we're going to be going counterclockwise direction for us. So the first thing that I'm going to have you do on the piece of paper that you have, you'll notice that there's a table. And you are trying to complete the table, given your height above the ground at a given time. So we know that we are going to start this Ferris wheel at ground level. So at 0 minutes, you are going to be 0 feet above the ground. So what I'd like you to try and do here is, based off of the information that you know about the London Eye, go ahead and pause the video and try and see if you can fill out the table. Alright, so here's my table all filled out. Notice that at 30 minutes I am back at 0 because it takes 30 minutes to make one complete rotation around that Ferris wheel. Notice at 15 minutes I'm at 450 feet because that's halfway, so that's going to put you up at the top, and you know that the diameter of your Ferris wheel is 450. And at 7.5 minutes, well, that's half of 15 minutes, so that's going to put you up here. It's actually going over here, and that's going to put us halfway up, which would be 225 feet, so it would be the radius of your circle. So there we have our table. Next, what I'd like you to try and do is, can you come up with a graph of this, which is giving you the height of a Ferris wheel over the amount of time? So that means that along your x-axis is going to be the time, and my suggestion is that you go off of the information that you have here. So 7.5 minutes, 15 minutes, and you just kind of keep, I'm just going to go by increments of 15 here, and see if you can come up with a graph that talks about its height over a given amount of time. So go ahead and pause the video, see if you can come up with this graph. Alright, so your graph should look something like this. And I guess I want to kind of look at, I can't see your graphs obviously, but take a look at my graph that I have here, and I'm curious, does your graph look like hills or does it look more like mountains? And one of these is a little bit more correct than the other, and the correct one is more the hill shape. And Reason for that is because if you're sitting here doing mountains and straight, more linear lines, understand that if you pick 2 points on that blue line right here, the slope there would be the same as I picked 2 different points. That does not happen when you're actually going around a circle. If we're on this Ferris wheel and we start down here at 0 and we're trying to get all the way up to the top here, even if I just try and get to that 225 feet point, whenever I pick 2 points that are on that circle, the slope between those points is not going to remain constant. And so what we actually want to do here is with your graph, you want it to be, because your slope is going to be ever changing, you want to make sure that you have a nice, I'm just kind of going to make my line here a little thicker, but you want to have a more so like a hill type graph where you've got more of this curve graph when you're looking at anything that is representing some sort of circular problem. Alright, so now that you have this graph, now we're going to treat this kind of like our parent function for the London Eye. There are a couple graphs that are going to follow this. I believe, what is there, 5 of them? I'm just kind of taking a look real quick. 1, 2, 3. Or is there just, there's 4 more. Okay. So what I would like you to try and do now is you are going to have to alter that parent function a little bit. So there are a couple different scenarios to look at, and what I want you to try and do is, can you come up with the different graphs? So I want you to go ahead and pause the video and try and see if you can come up with all of the other graphs to go along with each of the scenarios. Alright, so now let's go ahead and take a look at the graphs, and then also with that I want us to think about what type of transformations are taking place with these new graphs that we have. So first one, after we did the initial one, was changing the diameter of the Ferris wheel. So what's happening here is this is changing your maximum height that you're going to reach. Originally our Ferris wheel went up to 450 feet. Well, now our maximum here is 200 feet. So you're going from 450 feet down to 200 feet. So that translation that's taking place there is you are doing a vertical compression. We're taking this function, which normally would have been going up much higher, and now you're squishing it down. So you're doing a vertical compression. And we're going to be talking about how that is going to be affecting what is called the amplitude. But right there, there's your vertical stretch or your compression. The next one here, you are changing on where you got onto the Ferris wheel from. And here, you aren't getting on at ground level. You have to kind of walk up a couple steps and get on. So in this one, some of you might have had a different graph, but because you're getting on that platform, and that's where it's going to hit its lowest point, your Ferris wheel is not going to dip down and go below that 50 feet. So with it being the London Eye here and being the diameter of 450, our maximum height then that we're going to end up reaching here is 500 feet. Now the difference between our original function and this one here is everything's being shifted up 50 feet. And so we are doing here a vertical shift. We're moving our function up 50 feet. The next one here, taking a look at making one rotation to be 20 minutes versus the 30 minutes. This, if you look at here, hopefully you see that this is going to be a horizontal compression then. Thinking about 30 minutes, if that's how long it took, if I were to take, here's 0, at 15 minutes we would be at the maximum. We're about here, and then there's our 30 minutes, not perfect, but if you think about that graph right there, that green one, that's what the original function looked like. Now, by changing the amount of time, we are compressing this horizontally. Alright, and then there was one more, which, again, hopefully you were able to interpret this correctly here. you are getting on the Ferris wheel, so here's your London Eye, but then you are getting on at the 3 o'clock position, so you would have to obviously be on some sort of platform in order to get you up to that. Since we are going counterclockwise around our Ferris wheel here, we'd be starting at 225 feet, going up to the maximum, and then coming back down. Notice that it does still take 30 minutes to make one time around. This one right here would actually be compared to the original function. It doesn't change the height, it doesn't change the length of time, it's just changing our position, and it's not changing the position by moving everything up or down, it's changing just the spot on the circle, and this here would be working with a horizontal shift taking place in our graph. Alright, so now, with that being said, we are going to get into a couple new vocabulary terms to go along with what are called now periodic functions. We're going to take a look at what are called periodic functions, as well as some functions that are called, it's kind of a fun word, sinusoidal functions. So the first thing that I want to get into is, what is a periodic function? So a periodic function is a graph that repeats itself identically over and over. So over the right here, I have a graph that, as you can see, hopefully, that it repeats itself. And my highlighter tool might not be the best for me here, but if I look at that graph right there, and I just take one portion of it, if I pick it up and I move it over, actually I went a little too far, but you'll notice that that exact graph is happening again. That is a periodic function. And with a periodic function, we're going to be looking at some new terms. We're going to be looking at what's called the, I'm going in order here, period of a function. We're going to take a look at a midline. We're going to take a look at an amplitude. And we're going to take a look at a phase shift. And then that is going to transition us into working with our sine, cosine, and tangent functions. So what is a period? Period is the amount of time it takes to complete one full cycle. So when I look at this graph, again, over here on the right, I'm going to just start here. And I look at just one cycle, okay? How long is that taking? And so if I start along the x-axis right here, I'm starting at 0. And then it looks like it's going up until 6. So 6 units would be the length of our period of this periodic function. Now if we think about our Ferris wheel that we were just working on, taking a look at how long it would take to make one complete cycle, that would be the 30 minutes. How long would it take to make one time around your Ferris wheel? Alright, the next thing that we have is we have a midline, which a midline is a horizontal line which is midway between the maximum and the minimum values. So when you look at your graph with a periodic function, you're going to have a maximum and you're going to have a minimum. Based off of those, your midpoint is going to be in the middle of those. So if I look at my graph right here, it looks like my maximum is about, 3 is probably right here. So we're going to go we'll go 2.5. So we'll say our maximum right here is 2.5. And it looks like our minimum might be negative 0.5. Okay, so those are just the values that I'm going to use. So when I look at those two, how am I going to find the point that's in the middle? Well, if you remember how to do your midpoint formula, so 2.5 plus a negative 0.5, and then divide that by 2, that would end up giving us 2 divided by 2, which gives us 1. And so here our midline would be at 1. Now, it is a midline. Therefore, our equation, it's not just 1, it would be y equals 1, because it's an equation of a line. So by taking your maximum and your minimum, and we add them together, divide them by 2, that will find you your midpoint, your midline. Another way to think about it here is from 2.5 to negative 0.5. That is 3 units between the two of them. Half of 3 would be obviously the 1.5, so 2.5 minus 1.5. You could think of it that way as well. And then the next part here is talking about the amplitude. The amplitude is the vertical distance between the function's maximum or minimum value and the midline. So we just went ahead and we found our midline. And we know that our midline was at positive 1. So there's 1. And we, or at least I, came to a consensus that our maximum was at 2.5 and our minimum was at negative 0.5. So here's 2.5 and here's negative 0.5. So the amplitude is telling us how far it is from your midline to your maximum, which is going to be 1.5. That same distance would have to go from your midline to your minimum, which is also going to be 1.5. So the amplitude is that distance. Lastly, we have what's referred to as a phase shift, which is a horizontal shift. And that's really just taking a graph, and I'm going to just highlight over this. And if I wanted to pick this graph up and just move it to the right, that would be a phase shift. If I want to move it to the left, that is a phase shift. Understand that moving it up or down, that is not a phase shift. Just a horizontal shift to the left or to the right, that is what a phase shift is. So if anything you can kind of see from this, your transformations from back when we were in chapter 2, chapter 1, when we were doing graphing, those are going to be coming back to us. Alright, so now also in your materials you should have this graphic organizer, so you can go ahead and take that out. We are going to be just looking at sine and cosine today. We'll take a look at tangents the next day or so, and kind of filling in some information that goes along with this. So let's go back to your unit circle. Alright, so here's our unit circle. We are going to be, we're going to be trying to come up with our graph to go along with the sine function. Now, I've taken this unit circle that's over here on the left, and for all the coordinates, I've just been working with the y values that are associated with them, since those are all the sine values. So we have the sine of pi over 6, the sine of pi over 4, the sine of pi over 3. Now, as far as my graph goes down here, it takes 2 pi radians to make one complete rotation. So I'm going to go ahead and put 2 pi here. I've got 1, 2, 3, 4, 5, 6, 7, 8. Yep, I've got pi. So I'm going to put 1 pi here. This is going to be my pi over 2. This would be my 3 pi over 2. And then for purposes here, I'm going to make this pi over 4. This would be 3 pi over 4. This would be 5 pi over 4, and so on. I'm just going by fourths because it's a little bit easier. And 5, 6, this would be 7 pi over 4. Okay, and then as far as my y-axis goes here, the highest point we're going to get is 1, and the lowest point we're going to get is negative 1. So, I've got my highlighter here, and now we're going to try and work out this graph. Now, starting at 0, well, the sine of 0 radians is 0, so we're starting here. Now, what about the sine of pi over 6? Pi over 6 is 1/2 of a unit above your x-axis. So at pi over 6, which is going to be about right here, we are at 1/2. Now, if I were to take pi over 4, we are at square root of 2 over 2 units above your x-axis. Then if I go to pi over 3, that is the square root of 3 over 2 units above your x-axis, and these are kind of slightly off a little bit. And then I get to positive 1, which is 1 unit above your x-axis. Now, if I were to take and look at these points right here, so I'm starting at 0, I've got 1/2, I have the square root of 2 over 2, I have the square root of 3 over 2, and then I'm at positive 1. Well, what about if you look at the next part of this? Okay, so I'm just going to take 2 pi over 3, you're at square roots of 3 over 2. 3 pi over 4, you're at square root of 2 over 2. 5 pi over 6, you're at 1/2. And then we're back at 0. If I were to take all of these and put them onto our graph, oops, it brought over my instead of 2. Notice what's happening with these points. It's a mirror image of what we just saw in that first quadrant. And so there's your first 2 quadrants as we're going around. Now what's going to happen as we get into the third and the fourth quadrant, now you're dipping below your x-axis. And so now we're going to be taking these values, oops, sorry, come on. Alright, so now if I were to take each of these just one by one, you'll notice that it dips down below our x-axis, and then it's going to kind of come back around. That right there is your graph of your sine function. I know mine's a little bit kind of stretched out compared to like what you guys have there. Maybe actually what I'm going to do, since you guys are on the video, let's go to yours and I'll help you fill this out. I'm going to zoom in a little bit. Maybe. There we go. Alright, so here's our sine function. So our parent function that we're going to be looking at using here is f of x is equal to sine of x. You'll notice that on your x-axis you're going from negative 2 pi to positive 2 pi, and your y-axis it's going from negative 5 to 5, but we won't be using all of that. The sine function, one thing that's really important here is that it starts at 0. And as far as, and then it has to get back to 0 at 2 pi. Our maximum is positive 1, and I wish actually this was slightly changed here. I think what I'm going to do here is I'm going to change this, and I'm just going to kind of scribble out these values. I wish they weren't there. And let's put a 1 up here and a negative 1 down here, just for graphing purposes. It makes it a little bit easier. Alright, so you've got 0 to 2 pi. Here's pi. Right here, sorry, I'm just trying to get this so I can write a little bit better. This would be pi over 2. This would be 3 pi over 2. And for your graph then, we're going to start at 0. At pi over 2, you would be at positive 1. At pi, we are at 0. At 3 pi over 2, we're at negative 1. And then we would be at 2 pi again. And so your graph looks like this. And then it's also going to go into the other direction as well. So changing that y scale just so it stretches it out for you guys a little bit, so it's a little bit easier to see. Alright, so there's your graph. Then as far as our domain goes, your domain is all real numbers. We can take the sine of any value. We are restricted with our range, however, so our range is going to go from negative 1 to positive 1. So it's going to have to be within there. our x-intercepts, you will notice that we are crossing the x-axis at multiples of pi. So I'm going to put here, I'm going to go k pi gamma 0. And the one thing here is with your k values is k is any integer. So putting that there, so you would have x-intercepts at 1 pi, 2 pi, 3 pi, 4 pi, and so on, negatives as well. Y-intercepts, our y-intercept, we are going to be at 0, 0. And there are no asymptotes. Okay, so there are no asymptotes in this situation here. We do have an amplitude. I'll go back up to the graph here, and I guess first of all, I can get to that a little later. The midline, we do have a midline right here, and our midline is going to be at 0, and then the distance from your midline to that maximum right there is 1 unit, and so that right there is your amplitude, so that would be 1. Your period is how long does it take to make one complete cycle, and it's going to take 2 pi radians to make one cycle. Right? And the transformation part, we will wait on that until another day. So that right there is your sine curve. Now, if we're going to go into cosine, so let me get back out to, oops, sorry. All right, taking a look at the cosine curve and what that graph looks like. Again, we're making one complete rotation, so you're going to 2 pi, and I'm not going to label all of them because it's the same as we had. But this time you have to be aware that when you're looking at cosine, you're looking at all the x values. And it's not going to be as easy for me to show this, but notice that for the x values that we're starting with, you know, the cosine of 0 radians is 1. The cosine of pi over 6 is square root of 3 over 2. The cosine of pi over 4 is square root of 2 over 2. Cosine of pi over 3 is 1/2, and then we get to 0. Well, so then when I see these on a graph this time, it's going to look something like this, because now I got to flip it over onto its side. And then notice that all of a sudden we go, right when we get into the second quadrant, now you're working with negative values. And so now we're going down below to get those points. And so our graph for cosine looks just a little different. So I'll go back to here. Zoom. So let's take a look at cosine. So here we'd be looking at f of x is equal to the cosine of x. And I'm going to, again, change this out. This is going to be positive 1, and this will be negative 1. And get rid of those guys here. Alright, so this time you're starting at positive 1. And actually at pi over 2, it goes through your midline. At pi, it goes to negative 1. 3 pi over 2 goes to the midline again, and then it goes back up to 2 pi. And then we can do the same thing. It's a mirror image on the other side. So our graph is a little like this. Your domain is going to be all real numbers. Our range is going to be values that are between -1 and +1. X-intercepts this time are at multiples of pi over 2. So I'm going to put k pi over 2 on the 0. And one thing that you just have to kind of be aware with this, though, is that it's not at every value of k, because otherwise, if you did k is 2, that would be at 2 over 2, which is pi, and that doesn't cross over. So here it's going to be k is odd integers. So when k is an odd integer, then it will be crossing over your x-axis. So 1 pi over 2, 3 pi over 2, 5 pi over 2, and so on from there. As far as a y-intercept goes, our y-intercept is up at that maximum, so that would be at +1. There are no asymptotes to worry about. The amplitude is the same as with sine. We are going to be having our midline at your x-axis right here, and the distance from your midline to your maximum right there is 1 unit. So our amplitude is going to be 1. Our period of this function, how long does it take to make one complete cycle? That is going to be 2 pi radians. And once again, we'll talk about the transformations at a later date. Alright, so now, how do we, well actually not at a later date, because we're getting to that right now. Now, I'm going to go back into view. Now we're going to take a look at, well, how do you do transformations with sine and cosine? When you're doing a transformation with them, you are doing what's called a sinusoidal function. Okay, kind of a fun word to say. And the sinusoidal function is changing that parent function that we were just looking at, whether it is stretching it vertically to affect your amplitude, or if it's going to stretch it horizontally or compress it horizontally to change your period. And it's going to affect, and based off of just that Ferris wheel problem that we saw. There's not just one Ferris wheel that's out there. There are, millions of different Ferris wheels, anything from a little model Ferris wheel to the London Eye. And so there's a lot of different parameters that you can set on those graphs. All right, so now we're going to take a look at, well, what are the different parts of this? And if you can remember these parts from when we did our transformations, you'll be in good luck here. So the first thing that I'm going to start out with here is the value of A. A is, if you think back to it, this is referring to your vertical stretch or compression. Now, what the value of A also, it also could be a reflection over the x-axis. Based off of if it's negative. So A is going to be really important because that's going to tell us our vertical stretch or our compression. It's also going to tell us if there's any sort of flip that's taking place. Then there's B. B is going to be our horizontal stretch or compression. It is possible that we could see a reflection over the y-axis, but I'll be honest with you, we're just not going to be working with that so much in these examples. All right, then you have H. H is your horizontal shift. So whether we are going to the right or whether you're going to the left. And then lastly, we have K, which is your vertical shift. Now, these four things right here have a direct effect on the amplitude, on the midline, on the period, and things like that, which leads me to here. So here is our graphs of sine and cosine, and we know that both of these functions here have a period of 2 pi. Well, the value of b in both of them is going to tell us whether that 2 pi is going to be bigger or if it's going to be smaller. And remember that based off of b, it's the opposite of what we see. So like if I had something like a 5 right there, that is going to be doing a horizontal compression by 1/5. And so here, your period, by taking 2 pi and dividing it by b, that will always give you what your period is going to be. So if I take 5 right here, that would be 1/5 of 2 pi. So that means that our period, which was 2 pi, would now be 2 pi over 5. So 1/5 of that. If I had b being something like 1/2, now remember, it's the opposite of that. It would be the reciprocal, so we would be doing a horizontal stretch by 2. And if I take 2 pi and divide it by 1/2, multiply it by its reciprocal, you would then get 4 pi. It would stretch it. Your midline is going to be affected by your value of k, because k tells you whether you move a function up or down. And our midline is right here on our x-axis. So by shifting it up or down, your midline shifts. So whatever your value of k is, that would be your midline. Your amplitude is affected by your value of a. And a is telling you what you're doing for your vertical stretch or compression. And your amplitude is always a positive number. Okay, if there was a negative number there, then there is some sort of reflection that's taking place, but that doesn't matter with the amplitude. The amplitude is always a positive number. It's telling you the distance from your midline to your maximum values. And so that's why I put the absolute value in there. And then there is your value of k, or your phase shift, sorry, and that's the value of h. So h is going to tell you whether you're going to the right or whether you're going to the left, and then that would be your phase shift. So I'm going to kind of leave it up to you if you would like to take a pause and finish the rest of this tomorrow, or if you're going to kind of do all of the notes today and then work on the assignment tomorrow. But I'm going to keep going with this video. And now we're going to be getting into the graphing of the sinusoidal functions. Okay. First of all, to make this probably the easiest for everyone is just being able to look at the function and be able to identify what the period, the midline, the amplitude, and the phase shift is. That's really going to help us. So, period. We know that period is 2 pi on our function. But now I see that there is this 1/4 right here, and that 1/4 is in that place of b. So to find our period here, we're going to take 2 pi and we're going to divide it by b, which is dividing it by 1/4. Sorry, not 1/2. And when we divide by a fraction, you multiply by the reciprocal. So really we're taking 2 pi and we're multiplying it by 4. And that right there would give us 8 pi. That's going to be our new period. So you are doing a horizontal stretch. Our midline, if I look at the midline, well, I'm not adding anything here, so our midline is going to stay at y equals 0. The amplitude is our value of a right here, and if I take the absolute value of 3, I get 3. And I am not adding or subtracting anything inside here, so there is no phase shift. Okay, so there you are. Okay, let's take a look at this one. Starting out with the period, we've got our value of b, which is 5. So we need to take 2 pi and divide that by 5. That's your period. This would be a horizontal compression. Midline, I'm going to take a look at our value of k, which is positive 3. That tells us that our graph is going to be moved up 3 units. The amplitude, looking at the 1/2 right here, the absolute value of 1/2 gives me 1/2, and so that's our amplitude. And I don't have, again, anything inside those parentheses, so there is no phase shift for this example. Alright, so what I'd like you to try and do here is, can you try and hit pause, try and see if you can do this one on your own. So go ahead and hit pause. So the period, you should get 2 pi. There actually is no compression, horizontal compression or stretch in this situation, because there's like a 1 out in front of that function, so you don't have to worry about that. Midline, we are shifting the function down 1 unit, so midline should be at -1. Amplitude is going to be at 4. There is a vertical stretch, and there is a phase shift in this example of pi over 2, which would be going to the right. Right. Go ahead and try and hit pause and see if you can come up with your values for this function. All right, and so for this one, we should get a period of 4, and be careful with this because your value of b is pi over 2. So 2 pi divided by pi over 2, our pi's are going to cancel, and then 2 times 2, which gives you 4. Midline here is at positive 5. It's being shifted up 5. Amplitude is going to be at positive 0.5. And then we are doing a phase shift to the right of pi over 4.